Game Theory Class 13 Video 1. In this video we're going to do an example to calculate a mixed Nash equilibrium. So let's begin. Okay, so the example is as follows. Here's some game, it's a 2x2 game, and the question is just to calculate all of the Nash equilibrium. So if the question says all of the Nash equilibrium, that means you have to calculate the mixed ones and the pure ones. Well, let's begin with the mixed ones. Recall that when you're trying to calculate the mixed Nash equilibrium, all you're after is a pair of indifference strategies. Mixed Nash equilibrium is a pair of indifference strategies. So the first thing I'm going to do is I'm going to work out the indifference strategies. And to do that, I need to work out the expected payoffs. So I'm going to label the probabilities P and 1 minus P, Q and 1 minus Q. And I'm going to work out the expected payoffs. So E1 of A, the expected payoff for player 1, if they play A, that's 4 times Q plus 1 times 1 minus Q. That's 4 times Q plus 1 times 1 minus Q, which is equal to 4Q plus 1 minus Q, which is 3Q plus 1. Okay? The expected payoff for player 1 if they play B. If player 1 plays B, they're going to win 0 Q of the time and 2 1 minus Q of the time. So that's 0 times Q plus 2 times 1 minus Q, which is just 2 minus 2Q. Let's work out all of the expected payoffs at one go. So let's keep going with the expected payoff for player 2 if player 2 chooses X. So now if player 2 chooses X, they're going to win 2 points P often and 0 points 1 minus P often. So that's 2 times P plus 0 times 1 minus P, which is simply 2P. And finally, E2 of Y, if player 2 chooses Y, they're going to win 1 point P of the time and 5 points 1 minus P of the time. So that's 1 times P plus 5 times 1 minus P, which is P plus 5 minus 5P, which is minus 4P plus 5. Okay, now that we've calculated all of the expected payoffs, we can use them to calculate the indifference strategies. So let's begin with the indifference strategy for player 1. Okay, so remember, the indifference strategy for player 1 is me solving for P. I'm trying to solve for this value of P right here. I want to know that probability. So to do that, I need to use these functions. I'm going to use these. I set them equal to each other. So I say E2 of X is equal to E2 of Y. Don't get confused because here it says 1 and here it says 2. This is just how the notation works. Okay? The indifference strategy for player 1 is the value of P, which makes E2 of X equal to E2 of Y, i.e. 2P equal to minus 4P plus 5, which is equivalent to 6P equals 5, which is equivalent to P equals 5 over 6. So the indifference strategy for player 1 is given by 5 over 6, comma 1 over 6. Okay, let's do the indifference strategy for player 2. This is when the expected payoff for player 1 is equal in both strategies. So E1 of A is equal to E1 of B. So we're using these two functions right here. So that's 3Q plus 1 is equal to minus 2Q plus 2. I can move the minus 2q over to the left to get 5q plus 1 equals 2, and I can move the 1 to the right to get 5q equals 1, and now I just divide by 5 to get q equals 1 over 5. So the indifference strategy is 1 over 5 comma 4 over 5, like that. Okay, we have our pair of indifference strategies now. So the mixed Nash equilibrium is given by big parentheses, and now we write player 1's indifference strategy, comma, player 2's indifference strategy. That's the mixed Nash equilibrium. Okay. Now let's think about the pure Nash equilibrium, because the question asked for all of the Nash equilibrium. Okay, so I'm going to use the quick method to work out the pure Nash equilibrium. I'm going to circle the maximum of the first numbers in each column and the maximum of the second numbers in each row. And whenever I have two circles next to each other, that's a pure Nash equilibrium. So I've got AX and BY. The pure Nash equilibrium are AX and BY. So this particular game that we're examining now, it has a mixed Nash equilibrium and it has a pure Nash equilibrium. It has both. Okay, and that's perfectly fine. So there's one more thing I want to talk about with regard to this example, and that's working out the expected payoff at the mixed Nash equilibrium. So I want to know the expected payoff for player 1 at the mixed Nash equilibrium. Okay, so to work out the expected payoff at the mixed Nash equilibrium, I can use the functions I already calculated. I already calculated these two functions here, right? You might be thinking, well, which one do I use? Do I use E1 of A or E1 of B? Well, by definition of the mixed Nash equilibrium, it's a pair of indifference strategies. It's made so that it doesn't matter which one I use. They should both give me the same answer. So all I do is I choose one of these two, and then I plug in the value of Q, which I calculated. So let's choose E1 of A. E1 of A is 3Q plus 1. So it's 3Q plus 1, but I know the value of Q. I know that Q is 1/5. So it's 3 times 1/5 plus 1, which is equal to 3/5 plus 5/5, which is 8/5. Okay, and just to double check and to prove that it doesn't matter which one I chose, let's try to do the same calculation with E1 of B. So E1 of B is 2 minus 2Q. 2 minus 2Q. So this is 2 minus 2 times 1/5, which is 10 over 5 minus 2 over 5, which is 8 over 5. It's the same answer. It doesn't matter which one I choose. Okay, to work out the expected payoff at a mixed Nash equilibrium, it doesn't matter which function you choose. Let's work out the expected payoff for player 2. At the mixed Nash equilibrium. So now I look at the expected payoff functions for player 2, e2 of x and e2 of y. Let's use e2 of x. That's really simple, it's just 2p. So the expected payoff for player 2 is 2p. And we calculated that p is equal to 5/6. So it's 2 times 5/6, which is 10/6. Okay? And that's the expected payoff for player 2. So at the mixed Nash equilibrium, one of the player 1 expects to win 8/5 on average, and player 2 expects to win 10/6 on average. So who's doing better at the Nash equilibrium? Well, you have to be good at fractions, I guess. 8/5 is equal to 1.6, and 10/6 is equal to 1.666 recurring. So this means that player 2 is actually doing slightly better at the mixed Nash equilibrium. So player 2 gets slightly more points at the mixed Nash equilibrium than player 1 does. That's the end of this example, and that's the end of this video.